Okay, by the way, do you have any doubt like regarding the previous sessions, previous discussions? If not, then let's start. So, first question.
Ma'am, can you hear me?
Yeah, I can hear you.
Ma'am, I had a doubt in the earlier assignment.
Okay, what was the doubt? Or maybe let's discuss that in the end if that is okay.
Sure, ma'am.
Okay. So, the first question is how to relate the directional derivative and the gradient vector. Hmm? Do you see any relation? Maybe you can recall your notes. It has been done in the lecture notes also.
Like the gradient vector is perpendicular to the tangent plane at the point.
Yeah, that's right. This is what geometrically it means, yes. But if you see them using the formula for finding the directional derivative and the way you write the gradient vector, I think there is a relation and that you can see. I mean, gradient basically helps you to find the directional derivative if you remember. Is that so? Okay, how is the gradient vector looks like? How to find that? Say, suppose we have f, it's a function which is given, let's say, in terms of x, y, z. I want to write the gradient of that. Can you compute that?
The gradient vector will have three units, like del f by del x, del f by del y, and del f by del z.
Okay. Yeah, this is how we compute the gradient and this is how we write the symbol del f x, y, z. Yeah, it's a vector which can be written like that. And can we find the directional derivative with the help of this gradient?
We dot product it with the vector in whose direction we want to find the directional derivative.
Right. I think what I don't know, there is in the lectures it has been taught like del f dot u denotes the directional derivative, but well, I think it can be also seen by if I write the vector u by norm of u. Right? It simply says that you have to go in the direction of u, but if I just scale that vector, it will remain in that direction, right? So I think this I feel that this should be the directional derivative of f at the point. Let's say you want to compute at point p at p in direction u. Let's say. So yeah, it's a dot product because del fp is nothing but a vector. This is a vector, and then you have to take the dot product. Yeah. So this is how we relate the directional derivative and the gradient vector. So gradient helps you to compute the directional derivative. All right. Second question is suppose we are given a function from R3 to R defined by x square plus y square plus z square and you have a vector in R3. What do you want to see is the instantaneous change of the function at the point in the direction v. if you follow the notes, then I think there I have written the recall part, but I should have hide this part recall. But you have to compute the instantaneous change of f at this point with respect to direction v, which is given to you.
We compute the directional derivative and
Yeah. So
place
can
the
you
values of the coordinate.
can you quickly compute and tell me what are the answers? Uh, Vishal, do you want to say something? If you see the way Sir has defined the instantaneous change, it is exactly the directional derivative at the given point with respect to the direction v. So this is just basically delta f dot u. But the point is here is this point is 101, and then v is the vector. So if you compute del f is 101 is nothing but del f by del x I cap del f by del y j cap plus del f by del z k cap, but you have to compute it 101. So what it would be, yeah, it would be 2 I cap plus 2 j cap plus 2 k cap. And then what is the instantaneous change?
The point is 1, 1 minus 1 for the other vector.
1, 1 minus 1, yes. Your vector is I cap plus j cap minus k cap. So del f dot v is 2 plus 2 minus 2, which is 2. So what do you have to find? The change or the directional derivative, and it's a scalar, right? You have a dot product of two vectors, it has to be a scalar. So this is what the change is. I don't know, should I follow the dot v without norm v, or I am not sure. Okay, maybe I will confirm this. Shall we write dot with v or dot v by norm v? Of course, direction is not going to change, but of course magnitude is going to change. So I am not sure how to.
Like when I referred to a YouTube video, I got one video from real analysis. There we had to convert a vector into the unit vector if it was not already given.
Yeah,
So
yeah.
here
This is
also the
how.
same rule should follow.
Right. I also believe that it should be norm v. So I will maybe tell you how this norm v is coming. I will tell you in a minute. So if that is the thing, then you have to just divide by norm of that, and then the dot product has to be taken in this way. So 2 I cap plus 2j cap plus 2k cap, and then dot with. So what is the norm for v? Yeah, what is its magnitude? The vector magnitude?
Root 3.
Yeah, it's root 3. So it's 2 plus 2 minus 2 by root 3, which is 2 by root 3. Okay, I feel this should be the answer, but okay, I'll confirm it. Hmm. So either somebody asks you instantaneous change of the function, or somebody asks you directional derivative, it is the same thing. One should not get confused. Okay, here are certain things that I want to say. This is how I um, to describe this fact, that how I think you know this, but let me just recall for a moment. You can see the surface, right? Fx equal to same. Very well, you can see the surface, and fixing a point P in the middle that I have fixed, there can be several curves you can draw passing through that point. Several curves. I have defined one curve which I'm writing CT. Okay, now fixing one curve, I can take the tangent at that point P with respect to that curve. So this is what C prime T naught is, and the point C prime C T naught is my point only. It's a point on the curve which I'm calling P at a let's say t naught, and the direction c prime t naught is nothing but the tangent to that curve, and it is also lying on the tangent plane to the surface also. You can also see as this becomes the velocity. If you have a curve, then c prime t naught will define the velocity of that particle moving along that curve. And assuming all these things, now if I'm just following the notations, so as sir also mentioned, if you assume the level surface, given that surface, you can always see the level surface, right? And then if you fix the any curve on that surface ct, let's say, then f of ct, if that surface, if that curve is on the surface, that means it will satisfy the equation of that surface. So f of ct has to be alpha. From here, I will just simply use the chain rule. What does the chain rule say? If you have composition of two functions, the derivative has to be the directional derivative, sorry, the gradient of that function at that point times the derivative of that inside function. And if that thing is a scalar, then that means derivative has to be 0. And this dot product will tell you that the c prime is it's perpendicular to delta f ct. So if I draw the curve c prime t the way I have drawn, you see the gradient is perpendicular here. And if your vector is perpendicular to a tangent to certain curve, then we also say that that vector is actually perpendicular to the surface also. So therefore the gradient vector is a vector which is always perpendicular to the surface. Okay, this is how certain thing that I want to say here. So another geometrically relation, one can say that the gradient is the one, it's a vector which is always perpendicular to the surface. So this is how one see geometrically. Okay. Again, I think this question is kind of repetition, so I will just leave this. So I just ask here, quickly, how will you say that? What is the directional derivative? Yeah, it is just the gradient times that. But again, this is not a unit vector, so we will first change. So at this point, so this is the point, sorry, this is the vector. You have to move along this vector, so you have to take the dot product with this vector, but this is not a norm one vector, so you just take the norm. And this will give you the directional derivative. Okay, so I just leave this part, it's a repetition. Fine, so this is one question which I find interesting. So as sir also said that directional derivative, it can be maximum, it can attain its maximum value, it can attain its minimum value, but in which direction will it attain its maximum? In which direction will it attain its minimum? That is something one wants to know. And that's not direct, but one has to see how. So I have written in the top the directional derivative of a function at a point along a direction, that is, it's a rate of change of function along the line in the direction of v. But of course, direction is not going to change if I change my vector to be b by norm b, right? So this is how my whole thing is that I want to take the dot product of the gradient with not just any vector, I mean the direction where I want to compute, but I will just take the norm one vector. So if I show you something, by the way, do you have any idea how to see this before I say anything? How to see this maximum and minimum value? Because look, the direction derivative is going to be a scalar and it can be maximum for certain directions, it can be minimum for certain directions. And value can also be, one wants to know that what is that maximum value and in which direction will that attain its maximum. Yeah, it's a valid question.
Also, ma'am, I think that when we are considering the rate of change in the direction of a vector, in that case, we should not consider the unit vector in that direction. because the magnitude of the vector will affect the rate of change.
True, I believe that this is true. But the instantaneous rate of change is nothing but the directional derivative then. That means that the way you are computing directional derivative, that would mean that you don't have to take the unit vector, right? I certainly believe that magnitude is going to change, but direction is not going to change. Um, okay, I will see this part. For the moment, let's assume we are taking unit vector. I will clarify this part, whether to take a unit vector or not. Oh, okay, let's come back to this direction thing. Yeah, so let's try to see this, how this is going to work. Del f at any point p dot u, assume that u is a unit vector. I am changing, suppose, the direction which I want to compute. That direction is it's given
Okay,
to be,
like
let
for dot product, there's the involvement of cos theta. So based on the angle, we can find the maximum and the minimum value for a particular direction, or in which direction it will be maximum, in which it will be minimum.
true. So therefore the maximum value is going to be attained. This is nothing but your directional derivative, right? The way we are following directional derivative. If I assume that u to be unit vector, the way I am saying, then you should be able to see that this equality is just del fp times cos theta. That means the magnitude or the highest value is being attained whenever cos theta, because del fp is fixed. I think del fp is fixed to us. We can only change the direction cos theta, the angle between these two vectors. That is in our hand. So as long as, so which direction which will it get its maximum value, that is easy to see, right? Yeah, can we see that?
Yes, ma'am.
Okay, what is that?
Also, like in this case,
Mm-hmm.
suppose like for cos theta, the maximum value is 1, the minimum value is -1.
Right.
But minus 1 is also equivalent to the change caused by +1.
Sorry,
So
-1 is also?
like -1 is also a change that can be equivalent to the change caused by +1. So should we better take mod of cos theta or the mod of the whole thing to determine the maximum and the minimum?
Well, a mod will give you one only, right? If you take modulus of cos theta, what would you get?
Like we are finding the direction.
We are finding the direction as well as the value also. Direction is being told by the angle theta, right? So if you see, the maximum is nothing but the direction of where the vector is parallel to the direction of delta fb. Do you agree that? So the
Yes.
direction of the gradient and the direction of that vector, if they are same, that means the angle is zero, and therefore you will attain its maximum. That the direction, if somebody wants to know the direction in which your vector should move, it should be in the direction of the gradient. And the value, if somebody wants to know, that this is how you will tell by the norm of delta fp. And cos theta, its maximum is 1, so it has to be only the norm of delta fp which will tell you the maximum value. Of course, the minimum is just the negative of that. And direction is also going to change. It will be the opposite direction. You see, if you are going parallel, then you are getting a direction in the same direction of delta fp, but if you want negative value, that means you have to move in the opposite direction to the delta fp. Yeah, vector, the maximum, the value, norm value, of course, is going to be the same. If I take the modulus of maximum and minimum, that will be same. But it depends on which direction are you moving. Are you getting what I'm saying? No.
Yes, I'm getting it.
Okay, if somehow if you feel that this is what I want to say, then can you please compute what that direction? Like anyway, we have said what is the direction, but still, I mean, you have to find cos theta in order to say the direction. I mean the angle, and you also have to say what is the maximum value.
So the maximum value would be the gradient of fp, norm of the gradient of fp itself,
Yeah.
and the
So this
minimum
is the
would be
max.
the negative of that.
Correct. This is how. Yeah. So if something you want, you are moving, let's say this is direction of delta fp, then your vector, whatever you are choosing, that should move. At let's say your u is vector at this point, then you have to move in this direction only. Suppose your vector is here, you have to move in this direction to get the maximum. But if you want to get the minimum, you have to just go the opposite direction to that. Then only your angle will be cos theta becomes -1, right? And then you will get your minimum value. Okay, so what is delta FP? The norm of delta FP?
Norm of the gradient of fp would be simply root of like del f by del x whole square plus del f by del y whole square plus del f by del z whole square.
Yeah, it is with the root, right? And in these things you have to compute at that point. I think what is given to you -2, 3. Yeah, this is the point I think. Yeah. So this value I think is going to be 4 times root 61. I think this is the value. So this is the maximum. So this fact will tell you that the maximum value of the directional derivative is 4 root 61. The value is clear, but you have to find the theta also.
So theta would be 0 degree for the maximum case.
Um, I well, just a moment. We have delta f p dot u is same as norm delta f p norm u cos theta. Therefore, cos theta is delta f p dot u by norm del f p. Isn't it this, right?
Yes.
So from here, uh, I think how do you compute this cos theta? Do you know u?
If it's given in this question, then we know it.
Well, I think I have not given. Still, can you be compute? No. Or yes?
Like if we are already considering that this is the maximum value,
Mm-hmm.
then it will be some k times the vector represented by the gradient.
Yeah, right. If I can forget u and if I can compute cos theta like del fp by non del fp, what do you say? Can I compute that? Like theta is nothing but cos inverse of this, and this should be the angle of your vector in order to say that it attains its maximum.
Yeah, we can do that.
Right? So if we can simply compute that this is what, I mean, we have to move in the direction of delta fp, then why don't we compute the angle which delta fp is making with the x-axis? Okay, that we can certainly compute like this. How? Because suppose this is your vector delta fp, you want to compute this angle, then this is nothing but this is your norm delta fp and this is your delta fp cos theta. So here you can tell, right? Anyway, so this is how your um, angle can be computed. So I am just leaving this part, but the whole point of doing is that the direction, if you want to know the maximum for the directional derivative, then it has to move in the direction of delta fp, and its value maximum is nothing but the norm of delta fp. That one can say. So yeah, this is certain conclusion. I'm writing the same thing. So let's leave this part. Okay, I just for the moment I will, yeah. Question is to compute dy by dx where function fxy is 0 is certain surface given to you, and then this is your fxy. Yeah, can we compute this dy by dx? You know, if y is in terms of x, I can certainly compute it. But we don't have that. Even then, can we compute this?
Using the relation for implicit condition, we can solve this.
Okay, so what will be the that condition?
So for the condition to work,
Mhm.
del y, del f by del y should not be equal to 0. And if that is true, then the value of dy by dx would be minus of del f by del x divided by del f by del y.
Is that so or something else? Something is you're missing, I think.
A negative sign would be there.
Yeah. Right. So you can still compute provided this makes sense. So can we do this by the way? Can you please check what is this del f by del y?
Del f by del y would be minus of e to the power x minus y minus 1.
Okay. And where are we computing? I think I mean I have to say certain points also. Where do you want to compute this dy by dx? Also, we can leave that part also anyway. So we have to make sure that this e minus, okay, minus ex minus y minus 1, this should not be 0. If this is not 0, then only we can compute. So we can write that fact that whenever x and y have this part non-zero, then we can compute dy by dx. And how do you say this? How did you get this, by the way? Here del f by del x is nothing but e power x minus y plus 2x. So it is simply this part.
This relation was derived from the chain rule itself.
Right. So if we have function f of x comma y being 0, then you remember f prime at xy is nothing but you have to, I mean, the f prime, I mean that del f df by dx. Okay. This one can compute by del f by del x into dx by dx plus del f by del y into dy by dx. So here, if we know that this is nothing but 1, hmm, and therefore from here you get d dy by dx is nothing but minus del f by del x by del y. So it is the application of chain rule, and what does it say? Basically, it just says that without even writing y in terms of x, I can still compute dy by dx, and this is something strange and something very, I think, interesting to see. Okay, so this is how we mean, and what I want to say here is the same thing. Okay, can we always compute the implicit differentiation for a function? And I think this is what just saw. This is what we call as implicit differentiation. You remember? This is, yeah, I have written, I think. This is implicit differentiation, and it doesn't, it has no meaning unless del f by del y is non-zero, right? So this is the sufficient condition in order to say that f has implicit differentiation or derivative, I should say. Now, can we see certain example where this is not true and therefore we cannot compute the implicit derivative?
Like if an expression f does not have y in the first place, then del f by del y would be 0.
Sorry, you want to say function has only x component, or
Yeah.
it's function of x only? Okay, so how to see that? If you have y equal to, I should say, fxy is same as x cube, let's say, then here we do not have any y component, and then dy by dx. What is the meaning? Like here, if you see del f df by dx is just 3x square. Hmm. It is, the meaning is like you can always write del f by del x into dx by dx is 1 anyway, plus del f by del y into dy by dx. Of course, this term is anyway 0, and therefore you just simply get del f by del x, which is same as df by dx. This is same as 3x square. Yeah, here this part being non-zero, I think this is what not I am not being emphasizing here. What I emphasize here is that mm, writing y in terms of x can help you in computing that. Here certainly there is no y, you cannot do that. But if suppose you have a function which contains y, but the partial derivatives come out to be 0 and you cannot separate that in order to compute the derivative, can we do that? I mean, the whole purpose of this doing this is nothing but without separating the function y in terms of x, even then we can compute provided del f by del y makes sense. Suppose this is 0. I mean, certain function where we can separate, but this is 0 and therefore we cannot do that. There was one example I think that has been discussed in the class. Okay, maybe we will come back to this later. So the definition, the statement of implicit function theorem is more precisely is like this. If you have an open set in R2 and you have a function from U to R, so that function is differentiable and partial derivatives are continuous. Uh, and this is the property we say function is C1 function if you know. And at certain point AB the function value is 0, and I'm saying that the partial derivative or the second derivative with respect to y, it's the same thing right that we were writing, right? So when we were computing dy by dx, we are saying del f by del y, del f by del y here. So then the only property which we are here mentioning is that the partial derivative of that function with respect to y is non-zero. Then we can find a certain interval, means in certain interval we can always get that y in terms of x. Yeah, there is a function phi for which I can write y is a function of x. It need not be true always, but it may be true for certain interval. But that interval must have this property, must have that the partial derivative has to be non-zero. Suppose it is 0, then can you justify that why it would go wrong? You cannot find a function such that it cannot be written as a function of x.
Ma'am, repeat the last part of the question.
So what I want to say here is that this whole theorem says that if you have function being differentiable and its partial derivative being continuous, then assuming that the partial derivative of that function being non-zero, you are saying that in certain interval you can write your function fxy as f of x comma phi x for certain phi as a function of x. That means you can write your y explicitly in terms of x. But this is only true whenever your partial derivative is non-zero and at a point, and then we are only discussing around that interval. So suppose this partial derivatives come out to be 0. Can we see some example where we cannot write the function as f of x comma phi x? That means you cannot find a phi at all such that y is a function of that. I mean, I'm saying that suppose I drop this condition of partial derivative being non-zero is not true, let's say. Then why it is going wrong? Why we are not able to we should have certain example where we can see that this condition is actually required. I mean, are you getting what I'm saying, or is it getting confused?
Ma'am, repeat once again.
Okay, so here is the fact. Suppose you have one function. I am just simply drawing any curve. And okay, I have to talk in R3 then, because we have 3 variables. I have to certain thing that I am drawing now here. What I am saying, suppose the partial derivative at certain point, let's say this is your point AB, and this has certain value, f of AB has certain value. The partial derivative, this is your f, suppose del f by del y, f is function of x comma y. Suppose this comes out to be 0. So can you give me one f, example of f, such that when del f by del y is 0, then y is not equal to phi x for any phi. That means your y should not be written in terms of a function of x for any function. If you should not be able to find any function. That means this condition is, I mean, this is very important for us to get. This is in fact sufficient condition. If you do not have this, you will not find y in terms of phi x. I mean, in order to write that in a neighborhood, of course, you should have this condition to be non-zero. But we, of course, we can also compute the derivative dy by dx without writing y in terms of x. Of course, if I write y in terms of x, you can quickly compute the derivative. But if I mix up the functions, even then you can compute, right? You could compute provided this is true. That means you are somehow writing y in terms of x and trying to define derivative, but very locally you are doing, very locally. It just says that you are doing it in a neighborhood of that point where this derivative is non-zero. So let me just clarify all what I'm saying through example. Suppose you take fxy to be x square plus y square minus 1. And if you see the partial derivative, what is the partial derivative of f with respect to y? Hello?
Yeah, ma'am. For which function?
Yeah, this function, what is the partial derivative?
It's 2y.
Yeah, and if I just look at one, you give me 1 point on this curve at which the partial derivative becomes 0. Can you give me 1 point?
Like any x comma 0.
Any x comma 0. I will choose 1 comma 0, right? Okay, let's see here 1 comma 0. If you see, I have taken a neighborhood of this, and suppose in that neighborhood of this, y is written as a function of x. Suppose this is the case. Then given 1x, you should be able to get 1y, right?
Yes.
But what is happening is here you are not getting 1 point, you are getting 2 points. Can you see that?
Hmm.
Here, if in this neighborhood, this point, it has value this function, it has value this function. So in a small neighborhood of this point, any small neighborhood you take, or in fact big neighborhood also you can take, at this point and this point minus 1 comma 0, you certainly cannot write y in terms of function, because first of all your partial derivative is going to be 0. Another thing is that if at all it is written, then it should have a unique value, but you can see that given 1x you have 2 points. A function can have a unique image, it cannot have more than one image for a given point. So this is how this condition is very important for us in order to find, and it is very locally what we are doing, very locally. I mean, if you see that there are, if you draw this curve, let's say if you fix 1 point here, you fix 1 point here, and if you see the circle cuts the x-axis only at 2 points. So there are only 2 points only which has a issue, and these are the only 2 points where the partial derivative of f with respect to y is being getting 0. And therefore, these are the only 2 points where in any small or big neighborhood of this point, you cannot write your y in terms of function. But why the issue is not for the other points? Because you choose this point, you have, anyway you can write your function. The upper equation for the circle is y is root 1 minus x square, and the lower circle is y equal to minus root 1 minus x square. And there is no issue, because if you try to draw a line parallel to see the y-axis in order to see how many times does it cut, of course it cut 2 points. But you can choose neighborhood, you can choose neighborhood small big enough such that it has a unique image, and therefore you can write y in terms of x, which I have written. Y can be written in terms of x. This is your phi x. So your function f of x comma y, you can always write f of x comma phi x. But this is only true for all the points except the 2, 1, 0, minus 1, 0. Is that, I mean, this is how what I want to say. Does it make sense?
Like we are choosing a neighborhood such that there is a unique image for a given x in that neighborhood.
Um, okay, the theorem says you can write y in terms of x in a neighborhood of that point where the derivative is non-zero. Where the derivative is non-zero. It also tells you, you can suppose you have these 2 points. If you choose these 2 points where the partial derivative of y is with respect to y of the function at this point are 0. Now you should conclude that your y cannot be written in terms of x by defining in terms of certain function. At all, if there is a function, then this is the function. This is the function. But you see, the above has root 1 minus x square as a function. The below has root 1 minus x square. Which one of will you choose as a by writing y in terms of x for this neighborhood? You see, there is a discrepancy in the sense at this point, this neighborhood, this curve is root 1 minus x square. This lower curve is minus root 1 minus x square. Which one will you use as to define that y is in terms of x? The above one or the lower one? Of course, things are clear if you go up, things are clear if you go down, but what is there in these two things, and these 2 points? And the whole thing is getting mixed up because your partial derivative is with respect to y is actually not 0. I mean, it does not satisfy that condition. Is anything missing, or is this okay, or do you want me to repeat something?
No, I understood what you tried to say.
Mm-hmm. Okay, let's go back to the statement which is important for us. First of all, this function has to be differentiable. Then only you can talk about its derivative. Partial derivative should exist because this is how we define the derivative of a more than one variable function. Partial derivatives are going to define its derivative. Now, but partial derivative can be zero non-zero. But you see, we saw an example where writing y in terms of x is not possible unless this is true. So what this statement is saying, that this property partial derivative has to be non-zero, and also it is very locally you are telling me. It may happen, suppose I take a curve like I take a curve like, right, let's say here you draw a curve and set another curve and like that. I mean, it may happen that at one point, if you see, there can be, it can touch the two things, 2 points at the same curve. Those things are a bit problematic all the time. So whenever you have, if you see, if you want to, if you want to see how many points will it cut the curve, just draw a parallel line to the y-axis. You will see how many points does it cut. If in a neighborhood you see there are more than 1 points, of course at that point you won't be able to write your function y in terms of x. So whenever your partial derivative is non-zero, then only you can write your function as a function of x. But it is very locally, because it may happen the curve equation differs. Yeah, the above equation may be different from the below equation. Or if you choose the different points, you'll get different curve equation, different y in terms of x. But locally, you would be able to write it, provided this condition is true. But we saw that if we drop this condition, you will not be able to write the function in terms of x. I think I'm taking so much time, but this is what I want to say.
Okay, so that
Okay.
by the theorem, it is proven that only when del f by del y is not equal to 0, we can find a neighborhood where y will be equal to fx.
Yeah, and if you change your neighborhood, your phi may also be different. It is locally you are writing your function in terms of x, locally, very locally. You understand this part? I mean, we want to write your function as completely in a function. If you see here, this curve which we draw, at this point the function has value 1 minus x square. At this point the function has value 1 minus x square. So minus of that. So this function differs once you choose different points.
And that's why for the entire function, there cannot be any y equal to fx in general. But in
Yeah,
a very small neighborhood, that would be possible.
yeah. So it is all about locally. Yes, I think you are getting what I'm saying. But this condition is forced to be there in order to write that. Yeah. And you see that you cannot even drop this condition by looking the example. Once you drop this, you have example saying that this will no longer be true.
Okay.
Okay. Yeah. Now we want to see the double derivatives, now double partial, mixed partial derivatives or double partial derivatives. How do you define? Suppose I know del f by del y or del f by del x. How to write del 2f by del x del y? And your
Like
function is
first we differentiate it in terms of x, then we take the result and differentiate it in terms of y.
which one are you telling? The first one or second one?
Like both of them will yield the same value.
Well, I don't believe that they will yield the same value. I mean, maybe it's true for this example that I have taken, but I am saying in general. I think this is our second question also. If you see uh, these two mixed derivatives, partial derivative, do they give always the same value?
They should.
They should, okay, but I doubt. Maybe we will see soon. We will see soon that there are examples where this will not be true. Maybe in between you also think if you can get an example. But let's try to find first d2f by del x del y for this given function. Yeah, can you quickly see that?
The answer is minus sine of x square into 2x.
Okay, let's compute. So, oh, sorry. The function is cos x square times y, and we want to suppose compute del 2. What are you computing? Del x del y or del y del x? So the meaning is you know partial derivative of a function. It is again a function actually. It's from R3 R2 to R2 here. What do? You
We
have the
consider
function.
the y terms to be a constant.
Yeah. So I think if you understand this, then this is nothing but del f by del y, and then you have to compute the del by del x of that function. This is again a function, so you can compute this. Therefore, it is meaningful to do that. Now, what is del f by del y? It is del by del x of cos x square only, and this is minus sine x square, and x square is 2x. Yeah, it's a composition of two functions, derivative of this and then the derivative of the middle one. Of course, in this case, what is the del 2f by del y del x? If I change my this, what is that?
The value we just calculated.
Okay, so let's see del f by del by del y of this function del f by del x. This is what the meaning is. The del by del y of x function. If I see y is a constant for us, it is minus sine x square into 2x. Now x is constant for us, so therefore y, the derivative is 1, so it is simply this. Of course, the way I am writing, this looks the same to you. So maybe you have this in your mind that this is always true. But I'm saying that this need not be true. Yeah, can you produce one example to see that? Do you think for some time you will get it?
Like right now, I'm not getting an example like that where they are not equal.
Okay, I think this is being written in the, I mean, it has been told in the lecture class that this may not be true. And there was also a discussion that when it is true. Yeah, if you can see somewhere, then I think you can. Okay, maybe we will see this example later. I'll tell you the condition first. So here is the certain result. So if function, let f be a function of two variable, f of is f of x comma y. Assume del f by del x, del f by del y, del 1 or del 2 f by del x del y, and del 2 f by del y del x. First of all, they exist. Hmm? And any one more property there should be then del 2 f by del x del y by del y. Can you guess certain property? What is that? Not just they exist, but they should have a property in order to have this. This is nothing but the continuity. They are not just exist, but they should be continuous. Then only this will happen. And you know the example which I chose, you see that partial derivative. See, they are product of sine and polynomial. Whatever partial derivative you choose is always going to be continuous, always. Yeah. So the example which I wrote, it is always true. But this condition, do you always say that this condition and this condition is always true?
Like not always
Yeah.
for higher dimensions.
Not even higher dimensions. I'm saying suppose I'm just taking function which suppose
Like
I
for one
define.
variable, it is a compulsory thing for something to be continuous at a point to be differentiable.
No, no, sorry, I'm not getting.
Like for a function in one variable,
Mm-hmm.
then it must be continuous at the point in order to be different, in order to even test for the differentiability.
Well,
Like for
differentiable.
one variables,
Mm-hmm.
then if a function in one variable is differentiable at a point, then it
Yeah.
is continuous at that point as well,
Yes.
automatically.
Yes. Therefore, the negation says that not continuous implies not differentiable.
Yeah, that's for one variable.
Yeah, but here higher variable, the property should go to the partial derivative. In order to have this mixed thing to be equal, that del 2 f by del x y and this del y del x, in order to say they are equal, this mixed derivative should be continuous. Not just they exist, but should be continuous. And I think you can construct an example where this is not true. I am not giving, but maybe you think about this. It is doable where one can construct if you know how to see an example which is not continuous. So you just form in such a way that you integrate that function once you get the function such that its partial derivative will not be continuous, provided you know that that function is not continuous. Yeah, I think if you know this function is not continuous, right?
Yes.
You know this function is not continuous. You know many other functions which are not continuous. Now can you get that function which you want to make sure its partial derivative is not continuous? Can you write another g such that del g by del x or del g by del y becomes one of these functions. Like that, you can say. Can you do that? I mean, just a help that I'm telling you, the way I'm telling you is there are several functions which are not continuous. So you can find a g such that its partial derivative become that function which is not continuous. And hence your mixed functions, that property may not be true. Are you following what I'm saying?
Yes, ma'am.
Okay, so remember this is not always true. If somebody asks you, then this may not be true. And the sufficient condition we also saw that to be true is that the partial derivatives, not just once, but both the degree 2 and degree 1 partial derivatives should be continuous. Yeah. Okay, now, well, we say that there is a Taylor's expansion with respect to a function. If I ask you to find the Taylor expansion of a function near certain point, and if I tell you a function value, can you relate those two things? Is there a relation? I mean, geometrically or not even geometrically, the analysis basically, the definition of saying it as a Taylor series, what does it say about that function? And why do we do that? I think if you see the lecture notes, it has been clearly mentioned that what is the significance of writing a Taylor expansion for a function.
Like we do it to make a function converge at a point so that we can get its exact value for a certain point.
Hmm. Well, you can say basically what is the meaning of being convergence? Like if you see, so you have a sequence. It converges to a certain point. You have a sequence of function which converges to a certain function. Suppose you have a functions, you have f and x such that it converges to f. The meaning is you are approximating your f by that sequence, isn't it?
Yes.
Yeah. So the state the statement that Taylor expansion is basically you are approximating. It's a this word approximation is quite deep in the sense. Suppose there are certain time when you do not know the exact value, but you know the approximate value, and we may not even need the exact value. Sometimes we can work with the approximate value, but provided we know how to approximate. So let me just write that the Taylor's expansion uh, is the concept of Taylor expansion is basically is to approximate the function value which may be very hard to compute, but function value hard to compute, but we can approximate the function value with the known values. The value which we want to compute may not be easy, but the way we know it, the certain values we may know, and then we can use those known values to compute the function value which we do not know how to compute. Okay, this is what I want to say here. So it is the approximation. This is the word which I want to say here. Now, and we also know how to find the Taylor expansion of a function around a point for one variable. But what is the Taylor's expansion for function of two variables? If you remember, maybe recall, a function of one variable f of x is nothing but f of a plus f prime a x minus a. It is at the point a you are around the point a you are approximating. Plus f double prime a by 2 factorial x minus a square and a by n factorial x minus 4n and so on. But here things were easy because it is one variable. How to uh, replicate all this series by in the two variable situation? Yeah, here the derivative, we do not have a scalar, just like in the one variable. If I write f prime a, it is a scalar, it is a scalar, it is a scalar. But in the two function of two variable, it's not a scalar at all, it's a vector. Yeah, the derivative is nothing but the partial derivatives vector, which is being described with the help of partial derivatives. So then, how to write then this expansion? Hello?
Yes, ma'am.
I think, let me just tell you directly. It's written in the notes also. So if you want to write approximate function in two variables, then of course you should start with a certain point as just like a in R. Here you start with AB in R2. Around that you want to write the expansion. Then you take the partial derivative. Instead of this derivative, since you do not have as a scalar, you have this as a vector, del f by del x at AB and del f by del y at AB. So you have to take the two components at the same time. So, but this is with respect to x, so x will come with this, and this is with respect to y, so y will come with this. So I will write like this: del f by del x, b x minus a. This is one factor plus del f by del y, again at the point AB into y minus b. Y minus b makes sense. Now this is the first part which is same to this part. This part is being changed to this part in two variable. Now can you say something about the second one? Can you write a similar thing?
Like, do we reproduce the same thing for partial derivatives as we continue?
Yeah, so for degree 2 you will get the mixed and the higher order derivative. So you will get the second order partial derivative with respect to x. Of course, now x minus a you have to take square, and then there is a 2 factorial here which you have to keep track. Plus now there are two mixed derivative xy and yx. But what we are saying is you can take one, because we are assuming at the beginning itself while writing the Taylor expansion, that the derivatives are continuous and therefore both are same, and therefore I can combine both, and then there is a twice which will get cancelled by 2 factorial, and then we are left with this term only, del 2f by del x del y a b x minus a y minus b. Now there's two things, so both factors will come, and 1 by 2 factorial is now for the other part, del by del y square ab into y minus b square and the higher derivatives. Does this make sense?
Yeah, it does make sense. And that means as we go on to the higher terms, the
Hmm?
number of subterms in each individual term will keep on increasing.
Yeah, and this is how we mostly write order of norm of x minus a comma y minus b, and order 3 and more than that. You see, the next terms have the power 3 or more than that. So we will just simply write, or sometime we write resolvent, or sorry, remainder or something like that. So R3x like that, right? But we know that remainder is going to be, after higher terms, it is going to be, the quotient is going to be the 0. So of course we can still leave by writing that much only, and this much is enough for us. Okay, since you know this, now can you quickly tell me the part B? Part B is first and second degree Taylor polynomials approximations for the function this. You see, the degree 1 and degree 2 polynomial in the Taylor's expansion, at which point will they come? If you see carefully the expansion which I have written, we have just now written, degree 1 and degree 2 polynomials are going to come till what point?
Degree 1 is the first term, and degree 2 is the second term, which
Yeah,
contains the second degree derivatives.
right. So first derivative, second derivative, that itself will give you degree 1 and degree 2. So can you quickly tell me the at least degree 1, leave degree 2. Let's write together. Yeah, this is all detail that I have written here. Power f of x is sine 2x cos y, and near the point 0, 0. So by definition, the expansion is this. Yeah, I think in the remaining terms I just simply write. Yeah, I think this is okay. So the degree 1 is being if you carefully see, degree 1 is this one which is contributing, and this is degree 2 which are being contributed. These are higher degrees. So for degree 1, let's say for degree 1, what is f of 0, 0? I think it is f0, 0 is 1.
F00 would be 1.
Yeah, so 1 plus what is del f by del x at 0, 0? Del f by del x is just 2 cos
That
2x.
would be 2.
Yeah, so yeah, right. So it will be 1 plus 2 times x plus what is this?
Del f of del y at 00 is 0.
Yeah. So the linear or degree 1 term in the Taylor expansion of your fx is this, is nothing but this. This is degree 1. And I think you can similarly compute your degree 2 and for the higher degrees. Okay, so you should remember this Taylor expansion, then only you can compute it. I think this is pretty straightforward. Okay, here are certain other questions. So What is the necessary condition for a point to be local minima or local maxima for a given f? This is necessary, not sufficient.
Okay, like I remember for one variable, for a point A to be either the local minima or the local maxima, it has to be one of the
Mhm.
critical points of the function.
What is the condition being critical point?
And we get the critical points by first taking the derivative of the original function and finding its roots.
Okay, so therefore this gives you critical points. Yeah, so this equation gives you critical points. And then how do you check whether that is a local minima or local maxima?
If we take the double derivative of the function
Double
and
derivative.
one by one we substitute the critical points in the double derivative.
Uh-huh.
If the answer for that is less than 0, then that is a local maxima, and if it's greater than 0, then it's a local minima.
Okay, so local minimum. This is true for one variable. Yes, this is what we want. Now, since we are in higher variable also, we want to see a similar condition. At least for finding the critical points, can you give me a condition that at least this should be true in order to have that point to be minima or maxima? At least that has to be true.
Like from this, like if I try to guess,
Yeah,
wait, I
yeah.
don't remember the thing right now. So first we take del f by del x, we get some uh,
Yeah,
like
that's
we
true.
find the critical, like we find the values of x and y separately.
The whatever you are saying, I think you are exactly on the correct path since you do not know the condition, but the way you are thinking is the correct one. If I want to change this condition that derivative has to be zero, how would I just simply do it higher dimensions? What should be the most suitable thing has to be done in order to have that? If I just a guess, I'm not asking anything more. I'm just saying that suppose derivative f dash x equal to 0 in the one variable. If somebody wants you to ask that how to change this condition in higher variable, what should be the most intuitive thing that should be there in order to make sure that this condition gives me critical points?
Like we take del f by del x to be 0 and del f by del y to be 0.
Exactly right. Exactly right. In the function of two variable, this condition and this condition, these both gives me critical points. You are completely correct. So your intuition actually worked. This is critical points. But as we know that there are many critical points, but not every point satisfy the local maxima, local minima, right? So among these many critical points, there can be maximum which there can be a point which will tell you local maximum, there can be a point which will tell you local minima. But just like we have, there is a criteria in one dimension that double derivative has to be this, then that certainly that point will give you maxima, that will give you minima. Of course, that similar thing should be there in the higher dimension and higher variable also. But this kind of thing, the double derivative, I think if you have seen the lectures, sir has not yet revealed this thing. Sir said that this double derivative criteria, he will tell in the towards the end that similar thing, just like double derivatives gives local maxima, local minima condition. Similar kind of condition will also be true for two variables. but yet we are not familiar with that, so I will not go into that thing. But there is certain kind of functions. There are certain kind of functions where this property, saying that it is a critical point, is enough to say what is the local maxima and local minima.
Like if we have a critical point, we can say that there is a peak or a trough in the graph at that point. But like for single variables, we have this the second derivative test to actually find whether it's a minima or a maxima.
Yeah, yeah. No, but we are trying to say that what should be the similar condition in order to check the critical points being giving a maxima or really a minima or nothing. I mean, does it always give, first of all, given a critical point, does it have to be local minima or maxima? It may not be, right?
It can also give a saddle point
Correct.
if the
This is
double
what I'm.
derivative is zero.
Yeah, so that's what I'm saying. I mean, for the one variable, you know that being there can be conditions saying that it is just a critical point is not enough to say that whether it is a certain point or not, minima, maxima. It should have certain more condition. But just like saddle points are there, which are critical, but which are neither local minima nor local maximum. Somebody is making a noise. Okay, so here, if I tell you there are certain kind of functions which we say convex or concave. Have you heard about this kind of function before?
Yes.
Okay, for one variable, do you know that? What kind of functions are these?
Okay, like for example, if we have a parabola which opens downwards, then that is concave down and convex up, like that.
Okay, and if I ask you these two functions, of course I have drawn the similar on the next slide also. Which one is concave and which one is convex? And what is the definition if you remember?
But concave and convex will also differ based on which direction we are considering.
Uh-huh.
Like if we consider the positive y direction with respect to the function on the right,
Okay.
then that is concave in the
Okay.
positive y direction.
Well, it depends where is the graph of the function, right? Suppose I shade up the graph. Then what do you say?
Yeah, these are concave functions.
Both?
Yes, one is concave up, one is concave down.
Okay, let me just. Okay, for you, what is the definition of convex? Let me write what I know about convexity. So we say function is convex provided f of tx1 plus 1 minus tx2 is less than equals to tf of x1 plus 1 minus tf of x2, and this should be true for every x1 x2, but t has to lie between 0 and 1. You remember, this is the condition being saying it is convex, and the inequality reverse if I say it is concave. And if I ask you that what is the line?
I'm seeing this particular relation for the first time.
Oh, really? Okay, let me then elaborate this part. This is very important somehow. And so tx1 plus 1 minus tx2 and tf of x1 plus 1 minus tf of x2. Do you see geometrically what they mean? If I start with t0, what is the point? Here and
T,
here. What is the point?
T0, it's at x equal to 0.
Yeah, t0 will give you x2 in the above line and sorry above part and f of x2 in the below part. If I look at t equal to 1, it will give you x1. Other one will give you f of x1. Can you say it is the straight line passing through joining x1 and x2 and f of x1 and f of x2?
It would be better if you elaborate on this one a bit.
Sure, sure, sure. Okay, if I write, so what? Let me write that equation again. F of tx1 1 minus tx2 less than equal to f of x1 plus 1 minus t of x2. So let me write what the meaning of these two quantities which I'm writing, this one and this one. What is the meaning is this: tx1 plus 1 minus tx2. If you draw this, t equal to 0 gives me x1, equal to 1 gives me, sorry, it will give me x2, it will give me x1. T f of x1 plus 1 minus t f of x2. T equal to 0, it would give me f of x2. T equal to 1, it will give me f of x1. If, or you can certainly say it like this also, x2 plus t time x1 minus x2. You can also see like f of x2 plus t time f of x1 minus f of x2. Now can you recognize these two things? Where t lies between 0 and 1? T lies between 0 and 1. You remember a plus tv? T is in R. What does it represent? Let me draw it once again. I think then you will be able to see. This is my vector A, this is my vector B. TV is certainly somewhere here. Somewhere on this vector. Here or here, I don't know. Somewhere here.
We use this thing while finding the directional derivative, while deriving the formula.
Okay, I understand you are, you know that, but what is the meaning here? Meaning is you have one vector A, you have another vector B. TV certainly on this line, somewhere. I assume that it is here in the right direction. It can be in the left also. Meaning of A plus TV by parallelogram is nothing but it is A plus TV. But where is A plus TV exactly? It is this vector, right? It is moving in this line.
It's a resultant vector of both.
Right. So if I vary my T, what am I going to get? If I vary T completely on R, so V is here, TV is moving in all direction, I'm saying, all direction. That means your A
Okay,
plus
like
T.
if we consider it in this way, like first we travel along A, then we travel along TV. So depending on the value of T, the final point will lie somewhere on this line, which is in the direction of V.
So you are saying everything. It's a line which is in the direction of V passing through A, isn't it?
Yes.
But if I restrict my T to 0 to 1, can you say it's a line joining certain endpoints? Yeah.
Yeah, for
If
T equal to 0, it would be
A,
A itself.
T will be 1, then it is A plus V. So it's a
Yeah,
line segment joining A and A plus V, right?
yeah.
Let's go here. Now can you tell what is this and what is this?
So we are calculating the x coordinate and the y coordinate for the endpoints of that line or for that
Correct.
line segment.
Yeah. So it's a line segment passing through joining x1 and x2. This is what the meaning of this is. Meaning of this is the line segment joining f of x1 and f of x2. Do you agree? We are moving, we
Or
are
like
starting.
if we phrase it in this way, it is the line segment from x1 comma fx1 and x2 comma fx2.
No, 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 no. This is one line joining x1 and x2. There is no fx1 here. This is another line joining fx1 and fx2. Do not mix up.
Okay.
Yeah, this is right. This is your V, this is your A, this is T. It is like starting with x2, moving along the direction. But T is this, that means it's not a line but line segment. Same thing here. Hmm? Okay, going back to what condition of saying it is convex. This is what I say, function is convex if and only if this is true. What is the meaning? When you take a line joining, this is nothing but line. Now, for us, this is a line. Whenever you take a line joining between x1 and x2, the image of that should lie below. This would mean below geometrically. I will tell what is that. Below to the line joining f of x1 and f of x2. Let me show you geometrically the meaning now. If I draw the graph, suppose this is what the graph you were also suggesting. Take the parabola. I take 2 points and I took the images. This is x1 and x2. I have to take 2 points. I will take this point. Um, x1 is this, x2 is this. What is the graph? Graph is f of x2 is this. This is nothing but my f of x1. Do you agree?
Yes.
The line joining x1 and x2 is here. And the line joining f of x1 and f of x2 is here.
Yeah.
Which one is below? Which one is lower?
If the x1, x2 is lower.
Yeah. The meaning is this itself. This that the line joining f of x1 and f of x2. The meaning is that this line joining f of x1 and f of x2 should be the above part. If I take the line joining between f of x1 and x2. So this condition geometrically means the line joining should be lie above to the line joining x1 and x2. This is what the saying that function is convex. Uh, um, but if I draw, let's say if I draw something like this, and if I ask you, if I give you 2 points, if I give you 2 points, um, this one, yeah, and this one. Now let's look at geometrically. The line joining x1 and x2 is this. The line joining f of x1 and f of x2 is this. The graph is okay. I have to tell you the graph. The graph is this. So can you tell the function is being convex or no? You know, the line joining x1 x2 should always lie below to the line joining f of x1 and f of x2.
Yeah, in that case, this with that logic, this is convex.
Oh, okay. Then I think I did something wrong. Say this. Yeah, this one. Graph is the curve. Yeah. Now, let me highlight that part because that is hidden now. This is one line. This is one line.
But yeah, but still the line joining fx1 and fx2 are higher than
Yeah,
the
but
line joining x1 and
ah,
x2.
true. Till this domain, everything is okay. You see, I think I should say this domain. Till this domain, your line is lying below to the line in the above. But what about this part? So, you know, such graphs, this is not convex. Not convex. Because um, if you carefully look at the line joining x1 and x2, this line and this line, for this part, for half of the part, there is a issue. For half of the part, it's okay. So you have to be very careful with the domain to which part you have to check. So this function is not convex, but if I draw completely this is convex. It's a mixed of concave and convex. It's half is concave, half is convex. And the condition of concave is just reversed. You just have to reverse this inequality by this. And therefore the line joining fx1 and fx2 should lie below them. Just like in this case, it should lie above. For concave, it should lie below. And that will tell you whether the function is concave or convex. I think you practice one or two function, you will get, I think. I think does it make sense or?
That does make sense.
Okay, maybe you see some example. It will be more clearer. And this fact you always remember that this is nothing but the line passing through A and in the direction B. All right. So, what was the fact here? What we are trying to say? Local maxima, local minima. So the sufficient necessary condition is that it should be a critical point, and therefore this should be the necessary condition in order to say that whether the point is local minima or maxima. But this will not give it is sufficient or not. Yeah, it's sufficient is not this. But let's look at certain function where one can make sure that this condition becomes sufficient also. And I'm saying that functions are convex functions or concave. Now, this definition of convex concave is only for the one variable. Now, question is what is the definition of function for the more than one variable? So, I think it has been done in the lectures also. Do you remember what is a function being convex or concave? If I correctly remember, it is del f of x y minus f of x naught y naught is greater than equal to del f by del x naught y naught x minus x naught plus del f by del y x naught y naught y minus y naught. I think this saying that it is function is convex, I think. And the inequality get reversed, then it becomes concave. If you reverse this inequality, it becomes concave. Suppose you have convex or concave function and a certain point is a critical point. Now can you tell the maxima minimum? Yeah, if you remember being saying it is a critical point, meaning del f by del x and del f by del y is 0. Suppose x naught y naught is that point at which the derivative is 0. Then the meaning is f is convex implies f of xy is greater than equal to f of x naught y naught for all xy, the domain of f. This is okay, right?
Yes.
And concave just reverse the inequality that f of xy is less than equal to f of x naught y naught for every xy. Now can you say, now can you find the maxima minima, right? Now knowing that it is a critical point, you will simply choose the value f of x naught y naught and say that whether this is local maxima or minima. So clearly for convex or concave, critical point is the point which will tell you the local maxima or minima. That means being a critical point is a sufficient condition for not for all functions, but at least for convex and concave. So we do not know how to find local minima maxima for let's say general function, but we know for convex and concave. Okay. Think, yeah, here is one example that this condition, this derivative being 0 is just a necessary condition but not sufficient to give a local minima or maximum. Look at this example. Your partial derivative del f by del x, take it 0, find the critical point. You take this 0, it becomes this. You take the partial derivative y, this will give you this. Now both equating and solving, you will get x and y both are 0. Now you should be able to get this function, it has minima or maxima. By assuming that this has only one critical point, it should give something, but we also know there can be saddle point. So this is the situation where it is a saddle point, you do not have maxima or minima. Why? Because local maxima, local minima, meaning that it in a neighborhood of that point, critical point. This critical point should give me local either minima or maxima in that neighborhood. But certainly I can find a neighborhood where the point 0, 0 is not neither local minima nor maxima. Why? Let's look at this curve carefully. Can you give me certain points in the neighborhood of 0, 0 where it is positive or where it is negative?
Yeah, at 1 comma 1 it will be positive.
Another point?
Minus 1 comma 1.
Okay, the one what you are saying, let's draw through that. This is what we are doing. 1, 1. You were saying about this point 1, 1. So if I have to use the word neighborhood because it is local minima, local maxima. That means only in the neighborhood of that point we are saying what is the maxima, what is the minima. So draw a neighborhood. 1, 1 point is bit far. Let me draw certain smaller point. Any point on this line, then curve becomes x square y plus y square x. It becomes 2x cube. If I take y to be x, it will just simply 2x cube. Yeah. If I go positive x, if I choose x to be 0, positive 0 towards, if I go positive, then it becomes positive. If I take x to be negative, it becomes negative. So clearly, as small neighborhood you give me for 0, 0, I can give you certainly many points at which function has maximum value and minimum value, which is neither determined by, none of them is determined by 0, 0. That means 0, 0 is neither local minima nor local maxima. But it's still a critical point. So the condition being it is a local minima or maxima, the necessary is that it should have partial derivative 0, but not sufficient. Not sufficient. It does is this okay?
Yes, it's okay.
Okay, and then what do we want to say finally? I think this has been done now. When do we say a function is convex and concave in 1 and 2 variables? I think we have discussed this part also. So roughly, and I think if you see this, in this one variable, it's simply easy to see. I think this is a question that we already saw. The points, if I draw the curve, then if I look at certain points, this point and this point, the line joining these 2 points and the line joining their function values, this lies above, that means it is convex. And if I take 2 points here and here, their images, this line joining is lying below to the line joining the points. You see, this function f of x1, this is f of x2. This is above, below, this is concave.
And
This
like
is okay.
as we shift the graph upwards or downwards, the nature will also change, even without
Yes,
rotating the curve.
yes, yes, yes. That is okay, right?
Yes, that is okay.
Geometrically, this is what the meaning is. You should just look at the line joining the points and their images. That will tell you everything. Okay. What is this about? This has been discussed. So I think We have discussed pretty everything that when do we have local maxima minima, we do not know for general functions, but we know for convex, concave, critical points are going to give me maxima minima, but not in general. Then we saw the convexity, concavity for one variable, that in that case we know that critical points and further their condition on double derivative, how to give maxima minima. We discussed the Taylor expansion, the approximation of function with certain values. And I just want to say one more thing here. I think that sir also mentioned, I like that thing, that here this part, if we see the function value, this sine 31, I certainly do not know what is the value. But I can write the function as this and use the fact sine a cos b plus cos a sine b. But without knowing sine 1, I do not know the value, or cos 1. But how to find sine 1? I will approximate this function around the point 0. So sine 0 is my a is 0 and x is 1. Sine x is sine a, sine prime a, sine double prime a, like that. I will approximate by this and then some approximate value. I will leave this as an error and I will find what is this and I will say that approximately these two things are same. Yeah, because this is 0, this is 0, this is 1. So approximately it is 1. In fact, it can be written for any degree x. So you do not know the value exactly, but you can write that it is approximately sine 30 plus cos 30. Isn't it? So,
These particular approximations were used in physics for
hello.
derivations. Hello.
Sorry, can you please repeat? Yeah.
Yeah, these particular approximations were used in physics for derivations.
True, but we also do. I mean, we mathematicians also do the same thing. We also approximate sometimes the functions. You know, the whole part of finding the Riemann integration, if you remember, if you have a certain curve, you want to find the area under the curve. It is all about approximation, right? We approximate the curve by certain partitions. I'll partition my uh, whole area, a whole part which I want to compute into the intervals. And for each interval, I will just simply approximate the function by certain function which we say upper sum, lower sum. And we take the difference. So even we also do the same thing. Sometimes we do not know completely the function values. If you see the Riemann zeta functions, their function values are very hard to compute. But certain approximations, inequalities we can get in order to know, yeah, roughly this is the value. So this Taylor expansion and this approximation, the whole concept of approximation is quite useful in general, I think. Just like you saw the function, one function is being approximated certain functions fn when we say that fn converges to f. That means you are approximating your small f with certain functions fn's, and you are coming close to your f. So these concepts are very helpful actually. And suppose you also want to know the integration f. Remember, if your function fn converges to f uniformly, then you can say it is same as integration of f, its limit outside. Although you can write this as integration of limit fn, but I'm saying that limit and integral you can interchange. That means you are approximating your integral value by integral value of this by taking limit. You understand this?
Yeah.
So these kind of things are very much useful, very much. Okay, I think I stop here. It's enough that we have discussed. So, and that one thing which I have a doubt, I think that I will tell you tomorrow or in the next class, that is it u or is it u mod binom u? I will see this and I will tell you how to relate the directional derivative and the gradient. To me, it is norm 1, but let's see. Okay, there is one more thing. Last time I asked you one question, that function which is continuous but not differentiable. on two variable. For one variable, it is mod x. For the other variable, I don't remember did I give an example or not, but just roughly comment, rough thing I tell you here that f of xy, if I remember, this function I think I told that it is continuous but not differentiable. I don't remember, but try this. Otherwise, if we will get time, I will discuss that how to prove that it is not differentiable but it is continuous. And mostly you have to go by definition. There is sometimes it's like partial derivatives are not going to help you because you know that certain partial derivative, even if they exist, function may not be differentiable. So it's not a sufficient condition but necessary. If you see here the partial derivative at 0 0 and for the y it both are 0, they exist, but f is not differentiable at 0 0. This is my claim, but function is continuous at 0 0. So try it, otherwise I will discuss the proof. Okay, that's all.
If for continuity, this rule was extrapolated to more variables as well. If we take the limit at a point,
Uh-huh.
and if the limit at that point is equal to the functional value at that point, then it's continuous.
True, true. I believe, yeah. This function has been defined whenever xy is non-zero, and zero if this is zero. This is how it has been defined. So you have to prove that limit xy going to zero, the function also gives me zero, because functional value at 0 0 is zero. So limit must be zero. Can you prove that? You know, proving that limit being same as zero, it's a bit hard as compared to proving it is not continuous, because then you have to just quickly find the paths which give me two different limits. But proving that it is actually continuous, that will be bit involved, in the sense like you have to play with inequality. I will quickly tell you how. In this case, it is simple. You take the derivative. So what do you want to say? Fxy minus function value. Suppose you want to check continuity at 0. This has to be less than epsilon for every xy minus 0 0 is less than delta. This condition is same as x square. It is actually the norm, but modulus norm is for us is this is what I mean. Whenever this is true, you have to prove this is true. Assume that it is xy. You consider the function. Your function value at 0 0 is 0. I am not considering that. Now, can you say this is less than epsilon using the fact this is less than delta?
Just a minute. Ma'am, could you show how to actually do it? I got confused
Yeah, yeah.
again.
No, no, it's okay. I will tell. Function xy mod x square plus y square. This is less than epsilon. Claim you have to prove this whenever under root x square plus y square less than delta. This is exactly the norm of x minus 0. Sorry, x comma y minus 0 0. Remember, this is nothing but x minus 0 whole square plus y minus 0 whole square. Okay, this way. Claim is this. Of course, without using this, I certainly cannot say, because you know this epsilon depends on delta. Sorry, the delta depends on epsilon. Sorry. This depends on epsilon. So let's see how. Let's see how. Consider mod x mod y. I can separate the mod and I can write this. Hmm? You know, there is one quantity which is similar to what I have in the delta. That condition, this condition is same. How to relate this is this: x and x square plus y square. Can you can you make an inequality between this term and this term? Yeah. Which one is more? Which one is less?
Like if x square is less than x square plus y square, so mod of x is less than root of x square plus y square.
Very good. Very good. So can I say this is less than equal to under root of x square plus y square? Under root of x square plus y square. Mod less under root. Is that okay?
Yes.
Are we done now?
Yes, we are done.
But what is your epsilon? But how would you choose your epsilon? Same as delta. I can do that, right?
Okay, like we have to choose ourselves the relation between epsilon and delta depending on the
Yeah, yeah.
condition, right?
Yeah. Given epsilon, there exists a delta. There exists a delta. Such that whenever that condition of delta holds, your function value is less than epsilon. So I say that this is less than, okay, given epsilon positive, there exists a delta depending on epsilon such that the function value is less than epsilon whenever x y minus 0 0 is less than delta. Hmm? So I
Yeah.
assume, suppose I assume that, yeah, then I can relate delta and epsilon and I can make that inequality true. So it is all about, you know, inequalities and how to relate the delta condition with your epsilon. That's all. But sometimes function can be a bit confusing and you may not be able to get it directly. But this is
Okay,
how.
like if we can also try one more way
Hmm?
in this one, like for example, like we know that root of x squared plus y squared is less than delta
Yeah.
or less than or equal to delta.
We keep it less than, strictly less than delta.
That means 1 by root of x squared plus y squared would be greater than delta.
Yeah.
And which means if I multiply xy to the numerator, then also the inequality will hold true itself.
Yeah. But this is xy, remember? Now how would you do?
No, like greater than delta, this thing.
Sorry. You said this is that what you want to say?
Greater than delta.
Oh, sorry. This is greater than delta. Well,
Which means like xy divided by root of x squared plus y square will also be greater than delta.
okay. This is greater than mod. Greater than this. This is greater than delta. Okay.
And like in this way, we find that the value for the original function xy by root of x squared plus y square that
Mm-hmm.
comes between epsilon and delta.
Well, if certain thing is less than delta, 1 by that is greater than delta. How? I know it is greater than 1 by delta.
Acha, okay. I think I think I messed up there.
Mm-hmm. No, I think maybe it can be done. I'm not saying that, but you can write it once and you can send me if you want. My email ID is this. You can send me if you want. So it's MAZ small 198753 at iitd.ac.in. If you want to share any proof, I will happy to see that and happy
Okay.
to communicate. Okay, that's all I think. So I think it's enough for today, and I will stop here. All right. So thank you, and see you next time.
Okay.